There's a very nice audience. I just hope not, some of you are not here because you mix up cosmology with cosmetology. That's right. That's where you put lotions on your face and so on, especially since the title is Wrinkles in Time. First thing about George you should know, and probably do know, is that he's a Nobel Prize winner. You know, it's I'll never forget that when I was in Stockholm with my wife, and I said to her, "Did you ever imagine in your wildest dreams that we'd be in Stockholm, you and I?" And she said, "You were never in my wildest dreams." Okay, I'll say a little bit about George, an old friend of mine, and I think that his achievements in cosmology are profound, and he'll talk a lot about that. In the materials I was able to find, actually, Google was not very informative. Usually you depend on Google, but there was a number of interesting things about him. One is he comes from a family of lawyers and judges, and that's an interesting background. And he commented on that, and also on a parallel kind of connection, because his mentor at MIT, where he got his PhD, was another friend of mine, David Frisch, whose son, Henry Frisch, is a professor across the street at University of Chicago, and is beginning to build a family of physicists. I'm not sure if physicists will ever last more than 2 generations before something terrible happens. But the incidence of judges is a very interesting one, because after all, law and science, and physics especially, but science in general, have connections of adherence to rationality. I think lawyers or judges in the law tends to look backwards in time at precedent, whereas physicists look forward in time for better funding. But that's a connection you can decide to go with or forget about. Let's see, what more can I tell you about him? He is a graduate of a daycare center in Auburn, Alabama. And then after that went to high school. I'm trying to remember the high school. Oh, that was in Ohio. That's right. His family moved to Ohio. He tells a lot about his mother's efforts to continue her education. Both his father and mother education was interrupted by World War II. His father is a beneficiary, as I was, of the GI Bill. Fantastic exercise in American wisdom. I don't know whether there's been an exhaustive study of what the GI Bill did for American science and American economics, but certainly millions of veterans went to college under the GI Bill who never would have dreamed of going to college without that help. And the country benefited enormously from the science and the industry and the economics of that large group of college-educated people. And we should recite that over and over again when we find that our society does not value education and science highly enough. Eventually, George found his way to a place called MIT. I don't know exactly where that is, somewhere up north, and got his PhD there, working in particle physics, and somehow then drifted into cosmology. Of course, these days we talk about cosmology and particle physics as sort of twins, or particle astrophysics is maybe the right name for it. And I think that if I lump them together, I think the expectations for major discoveries in our view of the world have never been higher than they are today. And so with that, I think I'll let George Smoot bring you to some of the exciting things that are happening in his field of cosmology. Thank you.
Thank you, Leon, and for the introduction, and IIT for inviting me here. And you might have noticed I changed the title from Wrinkles in Time because, you know, the aesthetics of the universe and the universe aesthetics are too close. And so we'll change it. But also we decided to change to sort of a more historical and open talk about where we are in cosmology rather than talking about right where we are today and what we've learned since then. And so I put this in sort of a general context in the cosmic scene investigation. They don't have CSI Chicago yet, but I assume you guys get CSI Las Vegas or something. And we're doing a very similar kind of thing. We're trying to understand what major events that happened in the past in the universe by looking for relic information and interpreting that and so forth. So I show you a picture of cosmologists at work. You might recognize them. You can tell that they have laptop computers and they have certain, you know, equipment with them. And people who do crime scene investigation and people who do cosmological scene investigation have a lot in common. The most important thing you do is evidence collection, but you have certain tools you use, and those tools include procedures, but they also include special things like telescopes and other devices to analyze the relics you have. And in fact, all of you guys can be involved in it. Look around the room and you'll see some of the relics left over from the beginning of the universe. And we've got to explain where everything in this room came from and why it got to be like this, including where the chemical elements came from and where, you know, why the certain abundances of things and so forth. That's the minor goal that we put for ourselves, just explaining everything. That's the kind of goal. So we have these procedures, but then we use computer analysis and simulations. That is, we collect the evidence using our tools and our procedures. We look at other things that we've seen happen by analogy and so forth, and make some guess as to what might have happened by analyzing the data carefully, and then we run simulations and compare the computer simulations with what we actually see in the world today. And those are major components of the analysis, and in Moore's law has made a lot of this possible. Of course, trying to simulate the whole universe takes a lot of CPU power. So there's one of our tools, the Hubble telescope, and this is the Hubble Ultra Deep Field. And if I push one of these buttons, does it get darker in the front? I make the front row of lights go down, or could you make the front row of lights go down? I'll try pushing buttons at random, but it might not work. And so when you look at this picture, if you're a science major, you should recognize that in this picture you can see 4 stars. You guys you could have just told me how to push the button. That's too many, but it's good. I'm in the dark and you guys are seeing the screen. Okay, so no, it's better without them. At least for this picture, it's better without the lights. Okay, so this is a star, this is a star, this is a star, and this is a star. There are 4 stars you can see in this picture, and you can tell there are 4 stars if you've ever studied optics or whatever it is, because if you've ever seen what a telescope image looks like, the secondary mirror on the Hubble Space Telescope is held up by 4 struts, and the optics are such that the stars are effectively like point sources, and they make diffraction around those 4 struts, and so you get this characteristic, you know, cross pattern from that kind of a configuration. And everything else you see in this picture is a galaxy. So that should give you some pause, because we're going to eventually explain to you that if you do a sort of a census survey of the galaxy, we see something on the order of 100 billion stars. And everywhere you see a star here, you see several galaxies behind it. So this should give you the idea there are a lot of galaxies, that if I could tile the whole sky with Hubble pictures, I would see over 100 billion galaxies in the visible universe. So the first question that should come to mind is, why so many galaxies, right? And these are clearly galaxies. Look at this. This galaxy it's a nice spiral galaxy, looks very much like our own. This is a nearby elliptical galaxy. You see these ones that are kind of a yellow color like our sun. Those tend to be relatively nearby, relatively late-tide galaxies. Behind it, though, you see these kind of spiral galaxies that are whiter, but these are also spiral galaxies.
but even behind those, you see some more irregular galaxies, but you see them actually at many different stages. So one of the questions is, how come so many galaxies? And the other is, where do they come from? And another question I always have, are there intelligent beings on this galaxy trying to figure out the same question? And there are a few of them looking at our galaxy trying to figure out what's going on over here. And so the question is, how come so many galaxies? And then how are the galaxies distributed? That's the beginning of our mystery story that we're going to try and reconstruct. Because if you thought about, well, if I was going to make a universe that was big enough for humans, certainly maybe you need a solar system, or maybe even a whole galaxy, but why would you need 100 billion galaxies? Why would you construct a universe with that many? That's an engineering problem. And if you had the clickers, you guys could answer the questions along the way. So I'm going to start the story about 100 years ago with Albert Einstein, who was known to be the person of the century. And it's not to say the story didn't start earlier. Really, it started 400 years ago that we had Galileo giving us the laws of motion and turning the first telescope to the heavens and starting to make discoveries that moved man from the center of the universe out to the peripheral aspect of it. And we've been moving that way ever since. And but the person who gave us the tools and the ideas to try and deal with the universe today is Albert Einstein. In 1915, he published the general theory of relativity. And all of you should know or should have heard the general theory of relativity, that you put matter and energy in the space, it causes space to curve, and the curvature of space tells the matter and energy how to move around in space. Well, when you allow a curvature of space-time, you automatically set in a scale, right? So it's easy to think about. Suppose I have a beach ball. It has a curvature to it. It has a scale, namely its diameter or radius, right? If I expand that beach ball up to the size of the Earth, it still has the curvature, but it's a different curvature because the scale is different. The diameter is much different. If I make the size of the sun, it's much bigger. If I make it the size of the universe, it's different, right? And so the idea of curvature implies scale, and the idea of expansion comes from the dynamics of solving the equations of general relativity. And there were a series of solutions. The first solution that made a lot of special noise was by Georges Lemaitre, who was an abbé in Belgium. He was an abbé in the Catholic Church. And he was actually trying to solve the problem of where the high energy cosmic rays came from, something that, and he hypothesized that it was a primeval atom when he found the solution that the universe could be expanding. A primeval atom that exploded, the primeval nucleus exploded and flung out all these particles. He misunderstood his own solution to the equation. The other person who found solutions sort of independently was a meteorologist working in Russia. He was very good at math, and he just sat down and solved special cases of general relativity equation, and he found equations that gave him an expanding or contracting universe, and that was really, you know, kind of cool. And he published it, and people didn't hear about it for a while. It wasn't re-evaluated after he originally published it until later on. And Einstein had a problem with Georges Lemaitre, because Georges Lemaitre not only made the news about this, but he sent him a letter saying, here's my solutions to your equation, and so forth. And Einstein wrote back, he says, your math may be tremendous, but your physics is abysmal. Because, you know, everyone knew that the universe was static, right? And you all know that. What do you call the things that move in the sky? Well, planets. That's the Greek word that means wanderer, right? And meteors, right? Those are the two Greek words. Everything else is the fixed stars, right? Everyone knew the stars were unchanging and the galaxies were unchanging, and therefore, how could you have a solution where the universe is expanding, right? And so Einstein looked at it and realized that not only could it expand, but it could contract, and so he went and said, what I have to do is introduce a force that balances gravity, so I introduced the cosmological constant, and I can therefore have a static universe. Well, it turns out it's an unstable static universe, but anyway, he felt better. And, but as soon as he did that, Wilhelm de Sitter, who was a famous physicist in the Netherlands, solved an equation for a universe that had only the cosmological constant in it, and that was a universe that expands exponentially. Expanding. And that, of course, made Einstein quite upset, because he thought that Mach's principle had to be right, and that would be matter and energy. And eventually, de Sitter and Einstein came up with a solution that was kind of the cylindrical finite universe by making the matter and energy just equal to the critical density. But that turns out not to be the universe we were in, although we thought till 10 years ago it was close to that. So here is
here's a picture of Einstein-Lemaitre at roughly the time the controversy was going on. And here in later years, after Hubble makes his discovery the universe is expanding, here's a picture of all three, the two of them in America, much older. And this is Millikan, who did the experiment to show the charged electron was quantized. And here's a picture of Wilhelm de Sitter and Friedman, just to complete out the cycle there. Okay, so the idea, and this comes from my student and my grand student, who wrote an article for Scientific American about the expansion of space and a lot of misconceptions, but we're going to suppress one dimension and imagine the universe is only 2 dimensions of space and 1 dimension of time, and consider it a closed surface, so make it like a sphere. Doesn't look so good on here compared to my screen. And as time goes on, the balloon expands, and the grid lines just expand with the balloon. And then if you look carefully at what a galaxy does, you'll notice this galaxy is on the crosshair, it's on the crosshair, it's on the crosshair. The galaxy doesn't move with respect to local space, but the space itself is expanding, and it's true for all this galaxy stays in the same coordinates on the coordinate grid. It's just the distance between the coordinate nodes changes with time. So what we think of is not this giant explosion of the primeval atom or the Big Bang that Hoyle wanted, where you have matter expanding out to existing space, but what we have is the space itself is what's expanding and dragging the matter along with it for a free ride. That's the critical idea, and most people didn't understand it except for the few people who were doing general relativity work and doing it carefully. But now that's the thing. So Edwin Hubble, American success story. He was a lawyer that had a boxer, and he got converted from being a lawyer to being an astronomer. And he made 4 major accomplishments, and the last of which was to become the second universal law. The first universal law that we had was Newton's law of gravitation plus the laws of motion added together. And the second one was the discovery that the universe is expanding. And that discovery that the universe expanded had to build upon the fact that he had to define that there were things called galaxies. Those galaxies were not inside our own galaxy, were as big as our own galaxy and far away. And then he started studying their distribution and then showed that they were moving apart. Exactly what you would get either in a big explosion or in the case the space itself was expanding. And we have evidence now that it's the space itself that's expanding. And so continuing on, we had to get to the chemistry. So in the late 30s and 40s, nuclear physics was undergoing a sort of a birth, and people were trying to understand it. And the question of where did all the nuclei come from came up. And George Gamow, who was an immigrant from Russia, came to the United States, started working on this problem and realized you had to have high energies in order to get nuclear reactions. And that's because you have to overcome the electrostatic repulsion between the protons or the nuclei. You have to get them close enough together. So you have to have high energies or high temperatures in order to get them close enough together. And so he realized if the universe was expanding, if you ran it backwards, as you compressed it, it would get hotter and denser. And that would be an ideal situation, very dense, very hot, an optimum situation in which to breed the elements. And so he had a graduate student, Ralph Alpha, working with him, and they worked it out. And they invited Hans Bethe to be on the paper so they could have the alpha, beta, gamma paper. It's a great joke. Only the scientists love that. And Bethe, to his credit, put his name on there. And in the end, because he was fighting with Hoyle all the time, and Hoyle was saying, no, it's all made in the stars, Gamow gave himself a 99 out of 100 because he predicted where 99% of the elements came from, namely 75% helium and almost 24% helium, and a smattering of lighter elements, but that accounts for 99% of the material in the universe, and only 1% of the stuff is burned and produced in the stars. That's a critical 1%. Almost everything in this room, except for the hydrogen and the water, was produced by burning hydrogen and helium in stars. And so as a result, he can work backwards from the abundances of those elements to predict what the temperature of the universe should be today. The universe had to be 1 billion degrees back when nuclear reactions were going on, because it had to have enough energy to put the protons together to make the heavier nuclei. And so we predicted that the temperature should be about 4 degrees. Here's a picture of Gamow in somewhat later days, and Alf and Herman in much later days for them. Bob Herman joined them, and they did that and redid the calculations, and they kept coming out with an answer that was on the scale of 5 degrees, and that work was kind of forgotten. A few people tried to study it and so forth, but then they gave up technology wasn't there, a lot of other things weren't there. But in 1964, Penzias and Wilson had been hired by the Bell Telephone Labs to follow up on the big experiment that they had done the year before, which was the launch of the Telstar satellite. So the idea was put a radio up on a satellite in space and see if you could detect it on the ground, see if you could send signals up to it and have it come back down to the ground and detect it. And so this antenna back here was designed to look at the Telstar satellite, which had an operating wavelength of 7.35 centimeters. And they hired Penzias and Wilson because they said the experiment was a success. Therefore, it would be possible to put communication satellites in orbit, but in those days, satellites were pretty weak and the amplifiers weren't very good. And so they had limited power, and they needed to know what the background noise was so they could figure out how many channels of communication they had to see how much money it would cost to make sure it was economical and so forth. So they hired Penzias and Wilson, who were radio astronomers and wanted to make a measurement in the 21 centimeter hydrogen line to sort of map out the galaxy and so forth. But when they were hired in, they said, we will try out this antenna with the existing high-quality receiver and prove there's nothing coming from the sky except a little bit of signal from the galaxy, and then we'll move to 21 centimeters. Well, they did a great job, and what they found was there was a uniform glow coming from the sky, and this turns out to be the relic radiation from the Big Bang, and they found its temperature was about 3 degrees Kelvin, not so far from 5, but outside the error bars of the measurement, and so the theory had to be revised. And so I heard about that at the time and thought, this is great, the Big Bang is the right one, and go back to my studies, doing particle physics and so forth. But then about 2 years later, Joe Silk, who was a graduate student at Harvard at the time and just finishing up, gave a talk and wrote this paper, and which was published in Nature in the fall of '67. And he gave this talk, and some of my colleagues and I went to it, and the thing is really summarized well in the abstract. One of the overwhelming difficulties of realistic cosmological models is the inadequacy of Einstein's gravitational theory, that's general relativity, to explain the process of galaxy formation. A means of evading this problem is to postulate an initial spectrum of primordial fluctuations. That is, if you're gonna make galaxies, you got to put some seeds in and you got to grow them, right? That's what any farmer would know. You need seeds to make it. The problem is, if you take this 3 Kelvin microwave background as being cosmological, that implies the fluctuations cannot condense out of the expanding universe until an epoch when matter and radiation have decoupled, which would be at a temperature around 4,000 degrees. Now, this is I'll explain why this is a problem in a second, and well, I'll explain it right now. So imagine I took you and I put you in the sun. What would happen to you? Okay, you vaporize, right? You burn, you vaporize, you don't have time to burn. There's not enough oxygen anyway. You vaporize, and you get ionized, right? So when the universe was above 4,000 degrees, it would vaporize you. It would also vaporize galaxies because you're clearly put together more tightly than galaxies, right? Otherwise, you'd be torn apart by galaxies, right? And so, right? So right away, you understand that. But now remember, if you go back to when the universe was even 1,000 times smaller than that, so 1,000,000 times smaller than now, it would be 1,000 times brighter than the sun, and you would just completely vaporize all the molecules, all of atoms, and the radiation pressure would spread them uniformly across the universe. Right? So even if you had the seeds for galaxies, they get spread pretty uniformly. But if you're willing to go back to when the universe is 1 billion times smaller, back when we were doing primary nuclear synthesis, making the hydrogen and the helium and whatever in the right abundances, you would find you blow the nuclei apart as soon as you get above that, right? That's why you didn't have the nuclei before. The temperatures are so great that the nuclei are blown apart, right? So not only are you ionized, but your nuclei is stripped of the nuclei. If you go back further, it gets worse, okay? So put a galaxy at the beginning of the universe, it's blown to pieces and doesn't do you any good. So then the question is, how can you make it so that these fluctuations would survive the primordial fireball to when you can actually make galaxies? And in this view, you cannot make galaxies until the universe is at least 1,000, has gotten down to the point where it's only 1,000 times smaller than it is today, rather than millions of times smaller that we think some of these other processes are going on. And this thing cuts off the bottom. But to me, this defined the mystery further by asking for smoking gun evidence of these fluctuations, but also saying, if this background radiation comes from the early universe, it would wipe out everything in the early universe, right? So how do you have stuff left now? And if it doesn't, what produced the uniform glow from a whole universe, right? What tremendous processes had to happen? So you had to have sort of two minds about it. And so I said, all right, this is kind of an interesting problem. My colleague said, this isn't science. These guys don't know what they're doing. They're just guessing, right? Which is true. But this is a place where if you went in and made measurements, you could actually, you had a, whatever answer you got, it was going to be important, right? And so I want to come back to it. So our cosmic scene investigation primary tool is that looking out in space is looking back in time. And that's because light has a finite travel time. So here's the Earth, and here's concentric spherical shells around it cut away. And this distance is the distance away to these objects in light years, to these shells in light years. And this is how long it takes the light to travel. And you'll notice that if something is 10 light years away, it takes 10 years to get here, right? It's good to use the right units. And so if we're on the Earth, it takes around 2 seconds to get something from the moon. You don't really notice that unless you're talking on the phone to somebody on the moon, and then it's kind of a noticeable delay. But otherwise, if you take a picture of the moon and it's what the moon looks like 2 seconds ago, who cares? Take a picture of the sun and it's 8 minutes ago, well, that's a, you know, you have to wait and make sure it doesn't blow up in the next 8 minutes, but then you're pretty sure that hasn't changed very much. But if you go out to Jupiter, it's 40 minutes, right? That screwed up navigation on the seas when people are trying to make good clocks, because they had to actually figure out the finite speed of light in order to correct that. But if you go out to the nearest stars, sort of the typical nearest 50 stars are 10 years away. So if you take a picture of a nearest star, you're seeing what happened 10 years ago, right? And but if you go towards the galactic centers thousands of years ago, if you go to the sort of nearby galaxies we saw in the Hubble picture, it's hundreds of millions of years to billions of years ago. And you can keep going out, but if you go out far enough, you're going to come to the point where you're looking out 10 billion years, and galaxies are just beginning to form. And you can look out even further, and you'll see the beginning of the universe, right? You'll see back to the time when the universe was hotter than the sun, or as hot as the sun, right? And that's what this sort of funny shaded area is supposed to be. And so if you were really a great cosmologist, you'd go out and get pictures of each of these spheres, and you'd plot them all up, and you'd have the time development, a sample time development of the universe, and you'd be all set, right? You can compare that to your models. And so here's the kind of how a picture looks. This is the Hubble. You know, here we're in this galaxy, spiral galaxy in the middle. You know, it's artist representation. And here are typical Hubble galaxies around us, and they're relatively nearby. And if we go further out, we see eventually back to the beginning of the universe, except we can't see back further. We can't see from the time the universe was roughly 1,000 times smaller back to when it's millions of times smaller, because it's opaque. It's like seeing the fog bank. You're seeing our cloud. You can see to the edge of the cloud, but you can't see through the cloud because it's opaque. So that's our issue of what's going on. So the other thing that's going on is that the universe is expanding as time goes on, and that stretches the wavelengths of light out. And so if you want to look at something like a star, if you look at a star when the universe was twice as small, the wavelength is twice as long. If you look at a star when it was 10 times, you know, smaller than it is, the wavelength will be 10 times longer, right? So you have to start building cameras that move out of the sort of the visible or the peak of the blackbody spectrum for stars and move to account for the redshift from the expansion of space and time. And so one of the tools of our trade is the same as it is for the CSI crime scene investigators, thermal imaging cameras. So we started building those. And so one of the very first one that was built, which tells you really the crudeness, because the Telstar one had a big corporation behind it. But when you actually look at the receiver, it was fairly advanced, but it wasn't all that fancier. So Dave Wilkinson, who was a new person at the Princeton University, began building apparatus to look at this. He'd actually been starting building it just before Princeton made the discovery. But so here's some equipment he put on top of the White Mountain Research Station, so on the California-Nevada border, and you'll see there's an antenna that looks at the sky and an antenna that looks at the reference load, and I'll explain that in a minute. And again, here are some antennas that look at the sky and look at the reference loads, and some secondary ones look at the sky just to keep internal reflections and so forth down. And this is what the equipment looks like set up. And this same basic design we use today, but we've made it a lot more sophisticated. So antennas looking at the sky, surrounded by ground screens to keep the radiation from the Earth. The Earth has a temperature of 300 Kelvin. We're looking at a radiation that's 3 Kelvin. And we're going to look for properties that are a small percentage of that, because the guess was if the galaxies can't start until the universe was 1,000 times smaller, if the fluctuations had to be 1,000th of what they are now, so that you had to see variations of a part in 1,000 of the 3 Kelvin. That's what the theorists were telling us at the time. And so you have one antenna look at the sky, one antenna that looks at your liquid helium or look at nitrogen coal load, and then you let the Earth's rotation sort of scan across the sky to make sure you're not happen to be on the galaxy or something else. And so this is the sort of next generation. This is what we began to call a differential microwave radiometer. We have two kinds, one that looked to measure the thermal properties of this radiation, the other looking for the imprint of those original fluctuations in case there should be. So we call it a differential microwave radiometer. You have two antennas as identical as possible, and you switch them very rapidly back and forth between them, and you put input in the receiver, and you look for an output that changes with the switching back and forth. So that means instead of having to measure the temperature of the sky to a part in a million over here and a part in a million over there and taking the difference, we just take the difference straight, and then we rotate our equipment. So this one is looking here that this one used to be looking at, and vice versa. The sign should change because you're doing the difference between the two antennas, but the signal from your equipment shouldn't change unless something happened during the rotation. So you start developing the techniques on how do you make more and more precise measurements. Right? And so we're sitting inside of a universe that's pretty bright, and we're looking for the dim part of the universe. So it took a lot of years to do this. So this is one of the first high-power devices that we built, and you saw the prototype that was standing next to the schematic before. This was used as an atmospheric monitor. It has a half-centimeter wavelength. This is the 1 centimeter wavelength antenna on one side and one on the other. It has corrugations. We mentioned this to some of the people. This is a way of controlling what electrical modes get into the equipment. And you design this to be on a rotating table so this whole thing can rotate around and interchange the horns. And then you have to put it up in space or up high in the atmosphere in order to see what's going on. And so the next thing you do is you enclose it in metal so that only the radiation can come in through the windows or through the antennas directly. And then you put it in a high-flying airplane. So there's a few of you that are old enough to recognize this airplane. This is a U-2 airplane. It used to be famous for making flights from Turkey to Scandinavia, and it flies extremely high, so high that the Soviets were unable to shoot it down, and very stably, so it takes beautiful pictures of all the stuff on the ground. And then there was an unfortunate landing that ended up creating the height of the Cold War, and several of these planes were then made available to NASA to do Earth resource survey. So you see all the various pieces of equipment. They're all designed to fit in the lower bay looking down, and here's ours designed to fit in the upper one looking up. So it's the one in the front because it's the only one. All the rest are cameras and infrared sensors and other sensors for monitoring, how the coastline is behaving and how the crops are doing and what forest fires are doing. And we're up trying to look at the sky. So, and this is a picture of the plane getting ready for takeoff. It's a spectacular plane. I won't talk about it so much. It's an incredible design. The same team that designed the SR-71 did it. This is Mark Ornstein, the first grad student to get his PhD on anisotropy measurements. And here's the best fit to our data map that we made of the sky, where we saw a variation across the sky at 3.5 thousandths of a degree. That is roughly 1 part in 1,000th of the radiation. We see this variation, and it very smoothly from 3.5 millikelvin warm to 3.5 millikelvin cold. And we didn't have good graphics in those days. This is back before computer graphics were outstanding. So we had a draftsman draw it up. We had a computer and the draftsman draw it up and fill it in. And we put the constellations on so everybody knew where they were. And, but you can see this. And so we could interpret this. We kind of expected to see a signal like this. We were also expecting to see additional signals. If the universe is rotating, you will see, just like when the sun rotates, it's more oblate, or the Earth rotates, it's more oblate on the equator. If the universe were doing that, we would see those kinds of it. We were looking for various effects like that. But we had expected a signal like this. We just expected it differently. So here's a picture we made for the Cosmic Background Explorer satellite. So here's the Earth. We're taking off from NASA Ames. So the Earth is rotating, and then the plane is flying. So at a few kilometers per second, there is rotation going on. The Earth is going around the sun at 30 kilometers per second. And the solar system is orbiting around our galaxy at a little over 200 kilometers per second, which is roughly 1,000th the speed of light. So you would predict that it should be warmer in the direction we're orbiting and cooler in the direction we're leaving because of the Doppler effect. Just simply the direction you're going, you run into more photons harder than the direction you're leaving, right? There's a frequency dependence and a solid angle sweep up. And so you predict it. Unfortunately, the direction we found was in this direction. And that, of course, made the astronomers freak out completely. And because if you look, there's known orbits of us in Andromeda. We know we're moving relative to towards each other at about 80 kilometers per second. or roughly 40 kilometers a second towards our center of mass, and there's some transverse velocity we don't measure so much. And at the time, there were 14 known members of the group. Now there are about 40. There's a whole local group that's not moving very much relative to it. So that meant not only is our solar system moving, but the whole galaxy is moving at roughly twice the speed the solar system is moving, because we're going counter to the direction we're going. So we're moving it at better than a part per thousand, this entire group of galaxies. Okay, so now there's another engineering problem for you, this where you need your clickers. If you have to take a group of galaxies, including us and Andromeda and a few others, how would you accelerate them up to 1,000th the speed of light without tearing the galaxies apart? So just in your imagination, go into space with a bag of feathers and throw the bag away and just spread the feathers out. Now accelerate them all up, right? What are you going to do? So the right thing you think is, well, I use gravity, and you say, let's count up what's around us, and there's the Hydra Centaurus supercluster, the Virgo cluster. There should be some acceleration in that direction, and you integrate it over billions of years, some acceleration in this direction. But when you add it all up, there's not nearly enough mass there. So you have to postulate there's this thing called the Great Attractor, right, that's out there. And then astronomers went to look for it. Eventually they found it, although part of it's hidden behind the plane of our galaxy. And then the question is, how are all those galaxies distributed? Now, if you remember back to the first picture, you did see some groups of galaxies, but you didn't look on a big enough scale to see whether you would see these superclusters of galaxies or even larger scale great attractors. And so this became a mystery because astronomers had sort of had a rule that everything followed the Hubble law, the expansion was great and smooth, and there couldn't be these peculiar velocities of this level. The physicists didn't have a preconceived notion, and they thought, well, the data says this must be what it is. It took another 10 or 15 years before the astronomers really accepted this, and this became the standard frame of reference. So we thought we'd better go on with our measurements, and so we designed the next generation. We figured we had to go higher, so now we had to go on balloons. I had been avoiding that because a lot of times the balloon stuff doesn't come back, or comes back somewhat damaged. And so we decided we had to go with a cool receiver. In order to make it fit, we went to a shorter wavelength by a factor of 3 so we can make it smaller. We cool it with liquid helium, point the antenna at the sky so the signal would come in this way, and then put a mirror that rotated reflected, so when the mirror was in place, it would reflect this part of the sky. And then we have the whole gondola rotate around. So that we're looking at two parts of the sky, but then we're chopping between. And then we rotate around and make a circle, and the Earth's rotation sweeps out a big part of the sky. And then we have to have a lot of ancillary stuff. And you hang this from the balloon, and near the surface, the helium gas ball is small, but as it goes up, it expands until it's about football field size. And then we have a parachute, and then we have a ladder, because you have to have something to torque against. Another physics problem. You just have to torque against something in order to be able to rotate without twisting up the parachute. And so this is the thing we made, and this is what the equipment that was in the cool part looked like. This is a 3 millimeter wavelength receiver, and here it is. You can see the corrugated horn again. And while we were doing this, there's another approach. Our competitors was Wilkinson's group at Princeton. Well, here's the final thing where we have the screen around it. You can see the window where you look in the horn. We've cooled the horn and all the equipment inside with liquid nitrogen and liquid helium. And if we had the horn exposed, it would condense water and oxygen on it, which would not be very good. And we even have a little thing we can flip up in order to calibrate during flight, in order to make sure things are going well. And the Princeton group had a grad student, Peter Salson, who, when I went to take this picture, immediately wanted to put his coat on, because, well, little did he know he'd be talked about today. But anyway, so it says Princeton here, but you don't know. So Princeton's approach is also to go to cool receivers. They cool the receivers here and put a window in at the switch, right? So that they kept their antennas warm, and they made conical horns by rolling metal, and then they made the flare in order to control the side lobes. They made the flare by going to the music shop and buying musical instruments and cutting the bells off, and then just clamping them on. So these are clamp rings for clamping the bells of the musical instruments on. And it always seemed poetic to me, but it also takes a lot of space in order to do this. So here is Peter Salson without his jacket, and Dave Wilkinson. It was a hot, humid day, getting ready for his flight. You can see the equipment, the ground screen, and the people from the National Center for Atmospheric Research putting on the telemetry and the ballast and so forth for controlling the altitude of the balloon. And here's what our gondola looks like going up, right? You see the bubble in the balloon that's going to expand to make the balloon essentially a big sphere, the parachute, and a long ladder coming down to separate, keep things far apart and to have something to rotate against. And so we were at a rate, we actually traded parts back and forth and we helped each other out, but we're also in a scientific competition to who could get their papers out first. And we ended up having 3 balloon flights. We were supposed to have 4, but sometimes the balloons don't come back. And we lost the balloon in the jungles in Brazil. We had 2 Northern Hemisphere flights from Texas, one that gave us this section of the sky, and one that gave us that section of the sky, and 1 flight from Brazil till the balloon got lost in the rainforest, and it wasn't recovered for over a year after that, until a palm heart poacher went into the jungle and is cutting down baby palm trees so that you could have palm hearts in your salad. It's a really sad story. And he happened to come across it, and he thought it was an alien craft, and he ran like hell, and didn't come back for 3 months. And then he came back with his machete and chopped off some pieces and tried to sell them in town. And they recognized it, and they called us, and we got to recover a lot of the pieces. So that's why we didn't fill this part of the sky in. But what we did do is we did see now, it's not a fit, this is the actual data. You can see there's a fair amount of noise, but you can see the warm region by the part in 1,000 to the cold region by a part in 1,000 on either side. And the fluctuations, which are mostly noise, but when you subtract away the dipole and you look and see how much there could be in rotation or in fluctuations on large angular scales, it's down below the part in 1,000. So we were down well below the part in 1,000, which meant that galaxies couldn't form if this radiation, if the radiation was true and was there back when the universe was 1,000 times smaller, it would have vaporized the galaxies from before that, so we couldn't do it. And so there got to be a crisis, and there got to be papers on this going on, and at the same time, we're doing experiments to see if the spectrum, that is, if the frequency dependence was the same. So we formed an Italian-American collaboration. So this is Giorgio Ceroni's group from Milan and a 12 centimeter wavelength measurement, and Reno Mandelese's group from Bologna and a 6 centimeter wavelength measurement. Our liquid helium code load on the ground here, me standing next to it. The 3 millimeter from Berkeley, the 1 centimeter from Berkeley, 3 centimeters, 1 centimeter, 3 millimeter detector, and then the Haverford College atmospheric monitor. And this is on White Mountain Research Station on a day when it was white. And back here are bristlecone pines, which are thought to be the oldest living things. And this particular young grove, the trees are between 4,000 and 5,000 years old for the older trees. Some groves where there are trees over 5,000 years old, according to the core samples. And so it's an interesting area to hang out, but I don't think that I live as long as the trees would. So we made measurements there, and then we went to the South Pole because it wasn't cold enough there, apparently. And so this is the remnants of the Italian-American team standing at the true geographical South Pole, not the ceremonial one, where the pretty pictures are taken. And this is a close-up, so you can tell it's me. It's my name, right? And the fact that we're sitting on 2 kilometers of ice, and I didn't have a white beard then. I had acquired that later to look more distinguished. And this was just white because my breath was freezing on my face, right? And we couldn't actually do it at the South Pole. It was a little too noisy there. We had to go a kilometer away where there was less interference from people, moving around and doing things. And so we had this really nice spot picked out on the ice shelf. Well, it's ice foam that's there. And we put our liquid helium doer in a hole in the ice, and we brought our liquid helium, liquid nitrogen. And we made a big platform and a wind screen and a ground screen. And we waited for a day when the wind was low so we could take our hats off so you could actually recognize us. And then we had a big pit where we could go and work on our equipment where it would be out of the wind and so forth. But it was sort of roughing it in those days. But we were there over Christmas, which is the sunny season, right? And people are there, and they've left their families behind. And so we had to come up with a scheme. And this shows scientific cooperation and management at its finest. You've got to figure out what can you send home that people would really appreciate. And you have to organize 40 people to go and lay down on 40 below ice. Right, and you have to have a certain amount of backup in case people leave, but you got to give them essential jobs like being a heart or a kiss, and and they got to lay there on the ice in the right formation until you can climb this rickety tower and take a picture, right? I mean, it's, who knows which job is the worst, right? But you'll also notice you're only as good as your weakest link. Notice the font here of this S compared to that S, right? I mean, so, but this is, this is a lesson in, cooperation and scientific, you're only as good as what you conceive and convince people to do and actually execute, right? And while we're doing this, we're starting to prepare the Cosmic Background Explorer satellite. So there's a COBE FIRAS measurement, which stands for Far Infrared Absolute Spectrophotometer. So FIRAS is much easier to say. So this is the antenna.
It's got the same thing. It's got an internal antenna that looks at internal load and an external antenna that looks at the universe. And you do a differential measurement, and it's a Fourier transform spectrometer, so you do a differential Fourier transform, the difference between the spectrum from the internal load and the external load. And then you have a universe simulator that you can pull into place. And this is a thing that we know to be 99% absorbing, and then you make it so that light coming in has to scatter 7 times before it can go back out again, so you know that it's essentially a perfect black body. So you adjust the temperature of the load inside so it gets the smallest interferogram you can get between the outside and inside, which turned out to be very close to null. And then you move the external calibrator in, and you adjust this temperature, you get a null again, and you read the answer off. And then you get to make the measurement. This is the theory. This solid line is the theory. And these are the error bars times 400. So the measurement is extraordinarily precise because it's that differential microwave radiometer kind of measurement that we spent so many years working on and so forth. And here's all the data. These are the ones from our White Mountain and South Pole measurements, these green ones. This is the original Penzias and Wilson. These are a couple of balloon experiments from the Princeton group. These are from the DMR experiment, which I'll tell you about later. You can actually measure the absolute temperature. And these are 2 cyanogen measurements. And then there are 2 measurements that are here. One from the fire-ass experiment, which is, was published essentially about 2 months after we had the COBE launch, and we did the measurements. And then we just refined it over time. And then about 6 months later, our British Columbia group flew a very similar instrument on a sounding rocket and got similar data, although with much larger error bars because they had much shorter exposure and a much smaller instrument to fit inside the sounding rocket. But all of these show you that over 4 wavelengths, or 4 decades in frequency or wavelength, that you have extremely precise. So now we have a full crisis. We don't have enough fluctuations, and we know that this radiation is really a thermal radiation and it had to come from the Big Bang. Right? So now we have the full conflict. And the thing that had happened is some theorists had made up some new kind of material called dark matter so that you could start forming the galaxies before the ordinary matter is released, so that once the ordinary matter is released, the incipient galaxy can do it, and then they could get a factor 10 out of it that way. And so now we knew that we had only another factor 10 to play with, and we had to get down there. So we started building, we continued building the Cosmic Background Explorer, COBE. This was a picture of what it was supposed to look like in the 70s. There were 2 experiments in the liquid helium door, one to measure the spectrum of the cosmic microwave background, and one to look at the first generation of light from stars and galaxies to see if Hoyle was right and do the accounting, right? Every time you burn a proton, a hydrogen and helium, hydrogen and helium to make the heavy elements, you get a photon out, and you can count the photons or the total amount of energy and do the checksum and see how much primordial material has been burned into heavier materials. And so that's what this experiment was about. And then the experiment that I was a principal investigator for to measure the spectrum, and we had 4 different wavelengths to begin with of the experiment. And so here is the diffuse infrared background experiment to look at the first generation of stars and galaxies. There are actually 10 different wavelength bands, and this is a picture of the sky, false color picture of the sky, taken at 1, 2, and 3 microns. And now you can see that we live in a spiral galaxy. Here's the nucleus of the galaxy, and here is the spiral arms, and this sort of fuzzy stuff is the dust. And then you see a few stars because we're actually in our own galaxy. So imagine the galaxy is a compact disk with a bulge in the middle, and we're out 2/3 of the way to the edge, and you're looking out through the disk. You'll see a few stars around you, but mostly when you look in the plane, you'll see a lot of stars. When you look in the opposite direction, you're so far out, there's very few visible stars left. So this is the anti-direction from the center. You have to wrap this around you. So this is the center. This is 90 degrees from the center. This actually shows part of the spiral arm we're in. Over here is the spiral arm in the opposite direction. So if I look at the center, which is like you, if I look at 90 degrees, then I'm in a spiral arm. Look down that way, I see a spiral arm. Look down that way, I see a spiral arm. And you'll see it a little bit more another. So, but when you look out here between the stars, you can look and see how much light is coming from the universe as a whole. And that turned out to be a little bit more than twice as much as what people had estimated it was going to be. And it's not that Hoyle was wrong or that more material got burned. It turns out a little bit more material burned than we thought. But in fact, a lot of the material gets reprocessed because very early some dust is made, and the photons that are absorbed from the starlight are absorbed and then re-radiated in the infrared, and you get extra photons that way. And so when you add it all up, you have to be careful to do the accounting. But we kind of know that. Since this experiment was done and those results came out, there has been a major survey called the 2-mass survey on the ground, which is survey the location of 500 million stars. So you can see, I guess it's ask for the light to go down. Can I turn the light down again, or is that too hard? So you can actually see two extragalactic objects on here. You can see these with your naked eye if you're in the right place. This is a large magnetic cloud, small magnetic cloud. If you know where to look, you can also see Andromeda if you look at it from the side of your head and move your head a little. But what you really see is the dust, and you see the galactic bulge at the center, and you see a lot more stars out here. But if you take these stars and average them into the bins that are like Derby bins and subtract them, you still see that you get a better match, and you see the extra pictures that are left, the extra events that are left behind. All right, we'll finish in the dark. Okay. So, and the Cosmic Background Explorer satellite started a long time ago. The group was formed in '76. There were 6 of us. There were 3 young guys that were the PI instruments, which turned out to be great because it took forever. And if we had been older, we wouldn't have made it. And 3 older people who were to stabilize us. And then in 1985, so 10 years later almost, we added a bunch more people. And as we got closer to the launch, we added some additional people. Here's a picture of the science working group in 1986. Everybody but one person is missing. You will notice the ethnic diversity is lacking, and there's not that many women, and there's not that many people of non-Northern European background or whatever it is. But you can see Ray Weiss, who was chair of the group, Mike Hauser, who was the PI of the Derby instrument, me, John Mather, Sam Golkus, and Dave Wilkinson, and then the second generation set of people that we did. There were a huge number of engineers involved. Goddard and NASA had been under sort of a hiring freeze for a while, and when Goddard got COBE assigned to it, got a chance to hire new people. So there were a couple of more senior people who took our designs from the balloons and the ground-based and the aircraft and started turning them into spaceflight versions and checking they were working. But we got to hire some young engineers. Some of them, Maria had literally just graduated when we hired her. And each one of these got one of the 4 frequencies. Each one of these people got one of the 4 frequencies to be responsible for. And he got responsibility for setting up the test and calibration facilities. And so that was a really young group that were really dedicated. They really took their responsibility seriously. And they went around, dealt with the senior engineers and did everything. It was just quite spectacular what they did. And it was a joy working with them. But there were all total, there were probably 1,000 different people that eventually contributed to COBE and making it go. So here's a picture of COBE. You can see a picture of some of them. Here's a picture of COBE from the very last time I saw it. This is it was tested and so forth at Goddard, but then it was shipped out to the Western Test Range to be launched from Vandenberg Air Force Base, which is near Lompoc, California. It's on the part of California that sticks out, so you can launch into polar orbit out over the ocean. So it's the westernmost point that has ocean below it, right? And so we had to move from being on the shuttle to being on an expendable launch vehicle. So we had to have a deployable shield. And you'll see here are the DMRs. This is a room temperature operating one. And these are ones that are cooled in order to get the sensitivity. I had to give up one frequency in order to do that. There's another one behind. And here's the problem for physics students. Here's a lid that you keep on the dewar to keep air and water from condensing on it. And you blow that off after you've been in orbit for a few days, so everything's outgassed, and you blow that off. The orbits will cross, isn't that correct? If the orbits cross, if they start at the same point, they got to cross. How do you keep from hitting yourself? That's the homework problem, right? I mean, you do not want to hit yourself with the lid, right? It would be bad. And even if you didn't hit that hard, it would still not be good. So since I lived on the West Coast, I had to come down and give inspiring talks and keep people working, but also do inspections. So I have a 2-hour videotape of me going around with a light source, making sure there's no holes in this and so forth. So this, I figured, was the last time I was going to actually see it up close and personal. It was the last time I saw it up close and personal, but I actually got to see it again, but not with this kind of resolution. It turns out it flies on a polar orbit where it's on the terminator, so it's in the sun. The sun is shining from this direction. This is actually in the shade. It's just illuminated. And there are solar cells on both sides of these things, and this rotates like a chicken in a rotisserie. The Earth is down below, so you're looking away from the Earth, and you're tipped back from the sun so that you scan this big circle on the sky. And as the Earth goes around the sun, it scans the whole sky out every 6 months. Right? And but because it's up there in the sunlight, when it's the winter time, you're on the ground in the dark, and you can see this thing coming over. It came across. It had exactly 14 orbits a day for the first 3 years of its lifetime, and before it started having a little drag. And so it always came over at the same time every day. You can go out and see it in the wintertime easily. Right? And so then we made a series of observations, and we saw the dipole. Now I'm in galactic coordinates. Here's the plane of the galaxy. The center of the galaxy is there. Here's the spiral arm we're in, looking one way, looking the other way. And then here is the part where it's warmer by a part in 1,000, cooler part in 1,000. Now again, this is real data. And then if you subtract that away and blow the scale up a factor of 100, so this is a part in 1,000, now it's a part in 100,000, you start seeing the galaxy is saturated. So it's hard to pick out the spiral arms and the galactic center, although it's there. But you start seeing blue regions together, a number of blue regions together, a number of red regions together, blue regions, and blue regions together. And that's an indication that we were able to show that there were variations out there, and those variations came from beyond our own galaxy and weren't coming from other galaxies, and therefore probably came from the early universe. They had the right properties to have come from the early universe. And the fact that you see groups of colors together tells you there are variations on more than one wavelength. You can imagine you have a large wavelength variation across the sky. It's cool here, it's warm there. And then you have smaller fluctuations on top of it. Where where it's warm and it fluctuates warm again, I see warm spots clustered. If it fluctuates down, I see it goes back to normal, I don't notice it. Likewise, if it's cool and it fluctuates cool, I see blue spots together, but I don't notice it going back to the normal so much. And so that's how you see that kind of a pattern. If you blank out the galaxy and analyze it, you start seeing that in more detail. You start seeing this grouping and the kind of structure, and you actually carefully analyze it, you see you have structure on many scales. So here's the history up until essentially today, although it's not the most recent WMAP picture, but it's a convenient one to use. This is what Princeton and Wilson would have seen in the sky if they mapped the entire sky. They mapped limited regions of the sky. They had a big antenna. Even though their wavelength was long, they would have sufficient resolution to see the galaxy with this resolution, and then they would see a uniform glow coming from the diffuse glow coming from the background. If you go with 100,000 times the sensitivity and subtract out the motion of the solar system, you see this map that Kobe made, warm and cool regions in groups, and you look at WMAP 2003 map, it has now parabolic dishes the way the Princeton and Wilson did. You see the galaxy much more resolved. You see this cool regions together, but you see additional signals on more scales, right, that you're seeing because you have better angular resolution. If you compare them same scale to same scale, the two maps are almost identical, the Kobe map and the WMAP, but WMAP provides you additional information. And we're thinking that later this year we're going to launch the Planck Satellite, supposedly October 31st, although I expect it'll be delayed 45 days, but we'll see. We'll have the Planck Satellite. Kobe had relatively poor angular resolution. WMAP in principle had better resolution, but when you had to subtract away the signal from the galaxy, you had to use the longer wavelength, and therefore you get a more smooth map. Planck has much shorter wavelengths and much greater sensitivity. It should have this kind of sensitivity, and this smudge is an indication it can also measure the polarization, which I don't have time to talk about, but you also should expect the polarization signal just from the fact that light scatters on anything gets polarized a little bit, and therefore you should be able to see and additional effects that would come along. And so here is the best estimate of the sky from the Kobe DMR 4-year data, right? And this is from the WMAP 3-year data. And here is what the world would look like using the DMR instrument. You would find most of the continents, right? I mean, there's Australia, there's, you know, Greenland, right? Probably Greenland ought to count as a continent by this kind of thing. But basically, you can discover the continents, and that means the great age of exploration is over. But there's still a lot of other things to discover. But suppose that it was the 1920s and you had this map, right? You'd be able to do geology better than anybody. You'd get continental drift really. By 1880, you could really do it, but I mean, you could be. So what we're hoping is having a map like this. But for a technical question, notice the difference between the kind of structure you see in this map and the kind of structure you see in this map. There's a lot of phase coherence across here. There's a lot of nonlinear processes going on in geology that you don't see in the early universe. The early universe is actually very simple. So far, we can do it all with freshman and sophomore physics. We don't need anything more advanced than that because it's all linear physics. It's all harmonic oscillators or linear kind of physics. Whereas trying to work out the details of the crustal movement of the Earth requires a little bit more than freshman physics. Right? Well, we weren't the only ones doing work. So this is a picture from the Sloan Digital Sky Survey of the location of the nearest million galaxies that they happen to see. So they just point their telescope at the sky like Hubble, and they take pictures. And Leon is remembering this because he was one of the architects for starting this survey. And you just point your telescope aside, take pictures, you throw away the stars, and then you estimate how far away the galaxies are, and you plot them here radial, they're they're just radial distance away, and you see things like this great wall of galaxies. You see places where there are voids of galaxies, where there are no galaxies there. And as the Earth rotates and you take a series of pictures, you get a fan shape across the sky. If you tilt your telescope to a different angle, you'll get a different fan across the sky. So you see two different fans here, and you see parts that's occluded because you're looking through our own galaxy, or because the telescopes weren't able to see that. Now I'm going to show you another one, which is a movie. So this is from the 2-degree survey, 2-degree field of view survey. And you'll notice the galaxies are in with their galaxy type and their color is when we know it. So we know some are elliptical galaxies, some are spiral galaxies. Now we're moving at about a warp a million. That is the mean travel time between that light takes to go from one galaxy to the next is around 2 million years. Right? So we're crossing in a few seconds, right? So really big warp factor. Now we don't see any galaxies here. That's not because there are no galaxies. It's because the survey hasn't looked there. Right? You saw some nice spirals zoom by. Right? Now you can start seeing what the survey has done. Start seeing that the galaxies are not uniformly distributed. You saw the Great Wall. You see this huge cluster of galaxies here, right? You know, when we sum all this up, are we going to get the right answer? Are we going to find that we're moving where we should be moving, you know, or something else? The answer is so far yes, but it isn't a completely done job. But it's done moderately accurately by samplings of galaxies in all different directions you can do. But so now we're beginning to be able to answer the question, how are the galaxies distributed? And it would be better if we had more angular resolution, more resolution on this screen. It looked great on my screen. But anyway, so now we got some idea how it looks. Now we're going to do the simulations because this only shows us the luminous matter, the ordinary matter, the stuff that we see in this room or our cells or in the stars. But in fact, there's a lot of dark matter. So I'm going to show you some pictures where the dark matter is shown in white and the ordinary matter is shown as yellow, right, just in order to differentiate them. If we look on the really large scale, this is 1 gigaparsec. A parsec is 3.26 light years. So this is 3 billion light years. On that scale, it looks pretty uniform like the floor, right? It looks pretty uniform. If there was or the carpet there, it looks pretty uniform. When you go down closer into the carpet, you'll notice it's a weave, but it's still a pretty regular weave. When we go closer into this carpet, you'll notice that it's kind of a web. Is it too bright in here? Should I turn the lights off again? And if you zoom in, you'll see where the web, where the random, you know, sort of, it's like a big spider web that got dirty. Where the web crosses, some of those places where several webs cross at once, there are a huge agglomeration of galaxies. So this particular one has somewhere between 10 to the 5th and 10 to the 6th galaxies equivalent in it, right? And then if we were actually able to resolve them and do the picture, you would get something on that sort of scale. Whereas out here, this may be only 1,000 galaxies, right? It's a tiny thing, right? So now we're starting to say, oh my God, the universe is really complicated. On a really big scale, it's really uniform, but on the small scale, it's aggregated up, and it's starting to look messy like the continents, right? Some nonlinearity is starting to happen. And that's true. The early universe seems to be pretty linear, but by the time you let gravity take its course for billions of years, it seems to mess things up. At least that's the kind of a story we're telling you. So here's the simulation that you get to fly through at warp a million. That white stuff is the dark matter that makes the galaxies before the radiation lets go of the ordinary matter so it can fall in. And here it is, right? And these things that are glowing kind of star-like, those are galaxies, right? Galaxies. And so you sort of fly through, there's all these sort of dark matter halos, and in the center of them there will be aggregations of stars or galaxies and so forth. This is going to fly around to see some of the intersections where you can start seeing clusters or superclusters of galaxies appearing. And of course they're going to zoom to the biggest and most interesting one because that's what the simulation is. This is a tremendously large, intense simulation. Moore's law barely solved it. So this is that supermassive galaxy as an example. You can see a filament coming in and a filament coming in and so forth. It's like the spider web is being reinforced around the matter that's been trapped in there. But you see a huge number of smaller galaxy groups that are floating around the whole thing. And that's kind of how we live. We don't live downtown like this. We live out in the boonies, right? And, in a small group of galaxies, even though it's 2 of us that are pretty big, but the rest of us are just insignificant, right? So we're going to zoom around and go away, and I'll skip that because I want to keep on schedule. I'm already running over, aren't I? So let me show you how that simulation is done. Okay, so this is a simulation done by Andrei Kosov, who's actually here in the Chicago area. And so what happens is the growth of the formation happens linearly with the expansion of the universe.
So if I start out with fluctuations that are at the 10 to the minus 5 level, because the fluctuations are at 10 to the minus 5 level, and I have to let the universe grow by quite a lot, so I might as well, it's pretty boring, nothing's happening, it's pretty uniform, it's like, you know, like a glass of water, there's not much going on in it, and it's slowly accumulating. And then when the universe is roughly 30 times smaller, so 1 plus this number is the size of the universe today compared to the size of the universe there. So the picture will start when the universe is 30 times smaller. The simulation, since we're doing a simulation, we're like God, we can look at it from all the angles. Don't be limited by our thing. And you can start seeing the cosmic web forming out of those initial fluctuations. And the formation keeps going on until the universe is about half its present size. And then you don't start getting larger scale structures, although they would be a little larger than this box. You just get the continued development of the filaments, and you get the slow migration of the galaxies down the filaments towards the nodes. Right? So if you look, you'll see the filaments are getting more and more defined in here, but that you're not getting additional long-scale filaments, partly because they don't go outside the box. But the larger simulations will do that. But you can see the kind of structures you get. And so imagine doing the simulation now with a much bigger box and many more particles. That's how you get the simulation that I showed you to fly through before. And it's a big, expensive operation. And you have to put in not only the dark matter, but you have to put in the fact that the expansion of the universe, in order to explain why you don't see the really larger scale stuff, you have to put in the fact that the universe seems to be accelerating expansion for the last about 5 billion years. That more recent epoch, for the first 14 billion years, that's how old the universe is, but for the last 5 billion years, the universe is starting to pick up speed and its rate of expansion, and that cuts off the formation of larger scale structure. So we have this picture that we have, well, I'll get to the quantum fluctuations, this period of inflation where the universe accelerates up to a very high speed, and as it expands and cools, it goes through a phase transition, and then it becomes to where gravity is attractive, just like our old friend, keeps us on the Earth and everything else. And the universe cools down and becomes transparent, and then the ordinary matter can start clumping and falling into the dark matter wells, and then you get the first generation of stars, and those stars and galaxies begin merging to make the more mature galaxies that we see in the Hubble picture. And we are pretty confident that this is 13.7 billion years ago, so better than 1%, and we know when these things happened with fairly great accuracy, just like we know this happens when the universe was 1,090 plus or minus 1 times smaller, right? So we're 1/10% kind of measurement in this kind of a calculation. So the Big Bang is well established. We get Nobel Prizes and princesses all around. So this is a princess I got to take to dinner, another one I got to take to dinner. We got a nice dinner. Leon remembers this, right? And you sit at the big table with the king and the queen and a few other people. But you got a lot of new physics that you got to deal with. Okay. So the composition of the universe, in order to describe it, is only 0.4% or 0.5% the stars that we see, things that astronomers study. There is a bunch of intergalactic and other kinds of gas out there, so the total of that's about 4%. And then there's about 23% of the universe that's dark matter, and there's about 3/4 of the universe is this dark energy that's causing the universe to accelerate its expansion. And who ordered that, right? Quote, Robbie, right? And so we have big questions. How did inflation happen? What is this dark energy? What's the dark matter? You know, we have a whole bunch of other questions now that are raised because we're successful. We're successful at the sort of getting towards the percent level. As time goes on, we'll certainly be at the percent level within 5 years or so. We want to understand what can come. And so, you know, on the back of your dollar bill is this part. They didn't tell you the secret stuff. This is the luminous stuff, right? The visible stuff. And there's the hydrogen and the helium that you know. But they don't tell you about the invisible atoms and the cold dark matter and the dark energy. Right? If you look on the back of your dollar bill, you'll see this symbol. The Masons really were keeping secrets, right? And we do have really connections between the quarks and the cosmos. And I'll give you a couple more examples. Even though I'm running over, I'd like to give a little bit more. So I got a joke for you, which I got on Valentine's Day, and I thought was so great. I used it in my talk on Valentine's Day, but then I realized it's so appropriate. So every Friday after work, a physicist goes down to the local ice cream parlor and sits in the second to last seat and turns to the last seat, which is empty, and asks a girl who isn't there, can you buy her an ice cream cone, right? Does this sound realistic so far, right? Okay, so the owner who's used to this kind of stuff, you know, weird university locally types, you know, keeps quiet, right? He thinks it's a little strange, but he keeps quiet. But on Valentine's Day, the physicist is emotionally distraught, and he really makes an extremely heartfelt plea and to the empty space. And the curiosity gets the better of the owner, and he says, I apologize for my stupid question, but surely you know there's never a woman sitting on the last stool, man. Why do you persist in offering ice cream to an empty space? The physicist replies, do you know basically, do you know quantum theory? According to quantum physics, empty space is never truly empty. There's all kinds of virtual properties coming into existence, vanishing all the time. And there's a finite probability that the proper wave function could collapse there, and a girl who's beautiful and appreciates me might appear, right? And the owner raises his eyebrow and says, really? Right? And of course, interesting, right? But couldn't you just ask one of the girls who's here already, right? You never know, she might, you might be able to buy her a cone. He says, what's the chance of that happening, right? Okay, all right. So the point of this joke is first to see you guys are paying attention, but second of all, that's what happened to the universe, and that's why we have hundreds of billions of galaxies, because the wave function for the universe materialized in a very straightforward way. We're going to take a region smaller than an atom, much smaller than an atom. There must be, virtual particles of uncertainty, and then we're going to expand that with accelerating inflation, and we're going to make real those quantum fluctuations. They're going to actually, because they're going to come outside their horizon, they're going to become real. And every one of those quantum fluctuations is going to turn into a galaxy or a cluster of galaxies. So our galaxy was once a quantum fluctuation that was smaller than an atom, right? And now it's a galaxy, right? And likewise, the Virgo cluster, which is thousands of galaxies, was once a quantum fluctuation that was smaller than an atom. It is now a cluster of galaxies. So that's the idea. So this picture is a picture of quantum fluctuations that have been blown up in two ways. They've been blown up by the 60 orders of magnitude expansion that space has undergone, truly the most incredible microscope anybody ever invented. And they've grown under the influence of gravity, so that the density fluctuations, it turns out the potential variations didn't change. Some of them got dissipated. The potential hasn't changed, but the density has grown under the attraction of gravity. But if you do it like a physicist should do and do it in terms of potential, nothing's changed. You just had the quantum fluctuation. It had the right potential. You made it as big as galaxy, and the galaxy poofed right there. It's just like the girl on the stool, only better, right? Okay, so I got a little plot showing you the evolution of a density, and you'll notice that I put a Gaussian density fluctuation in. I end up with a spherical shell going out. Remember, it's only 2 dimensions showing up. I get a spherical shell going out. How can this be? How can if I start with a Gaussian distribution, that it separates out like this? Well, it's exactly the thing I described to you before. So I'll now show it to you instead of in 2 dimensions, in 1 dimension. And try to show it to you. Okay, so I have to make a fluid, which is made of 5 things. It actually is made of 6. They're gravity waves too, but we neglect them because they just go out at the speed of light and they disappear. So we make this thing where we make it out of dark matter. We make it out of baryons, that is gas. We make it out of photons, and we make it out of neutrinos, and we ask what happens when we let go of them at the beginning of the universe. Right. So now I have to let go of them. Well, I've got to try and let go of them. And you'll see what happens. They separate. So let me show you what happens at 170,000 years. You'll see the neutrinos try to free stream out like the gravity waves, but there's some residual drag, and they only go out. The dark matter pretty much stays in a lump, and there's only a little bit of Boltzmann tail of things moving around at high speed that kind of leak out. But the matter and the radiation, the ordinary matter and radiation, are tightly coupled, and they move out like the sun puffs up right under the heat, right? And so that will happen as the universe expands out to about 400,000 years, and then the universe becomes cool enough for neutral atoms to form, and the cross-section for scattering goes from Thomson's cross-section to Rayleigh scattering. It drops 14 orders of magnitude. And the radiation comes separating out, and the ordinary matter begins to fall in the potential wells left by the original perturbation of the gravity waves. And so as it goes on, you see the radiation goes out. Now the image we make, the bumps you see on there are in fact, so let me stop it here. You will see the ordinary matter has fallen in the potential well defined by the dark matter, except for this little bump left out here, which are the baryon acoustic oscillation residuals. That if I have a cluster of galaxies and I look out at 150 megaparsecs, something I can calculate easily, what's the speed of sound in the early universe? Well, it's the speed of particles divided by the square root of the number of dimensions, which happens to be 3. Then the speed of the particles is photons, so it's the speed of light divided by root 3. So I can predict when that last scattering surface is. It's at the 400,000 years. I can predict that accurately.
right? I can predict all this stuff. So I can predict exactly how big this is in present dimensions. So I can look 150 megaparsecs, or 4 million light years, 400 billion light years away from the center of the cluster. I will see some extra galaxies out of the few percent. And this has actually been seen, right? So we know we're on the right track here. And we can use this to teach our students that the Earth is round, but the universe is flat, because we have a sound horizon, whose 150 megaparsecs radius. We can look at that. If the universe is flat, right, we have side, 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 so we know the angle. That's what you learn from But now imagine the universe is positively curved. If you start on the equator and you project two things perpendicular to the equator, they will meet at the pole. So there's convergence. So when you extrapolate back, assuming Euclidean geometry, you'll think it looks bigger than it really is, right? So your spots will look bigger. And if it's the other way, if it's like a funnel where the things are coming apart, you can also do that, and you will see the spots should look smaller because you're extrapolating them back to smaller. And then you can compare that with what you see. And what do you see? Well, you can make you can make a calculation of how these peaks should move. This is the peak that's that first oscillation. And you can measure what you see, and you see this peak, which shows up just below 1 degree scale, around 220, L equals 220. And then you see harmonics of that, right? This is almost the current state of the art. The WMAP released the 5-year data, but I didn't upgrade my plot for that. But this is basically where we are in the state of the art. So we can just compare that to models of the universe, computer models of the universe, where we allow the curvature, which just causes this peak to shift and causes some low stuff, or one with a cosmological constant. If we put extra baryons in, it makes the first peak go high, the second peak go low, the third peak go high. If we put more matter in, it makes all the peaks go higher. So you can separate out what the various components are, and I can make up a table, and I can tell you what the universe is made out of, what its expansion rate is, that it's extremely close to the critical density. That means it's very flat, that all the matter added together is only 27%, that the ordinary matter is 4.4%, the dark energy is 7.3%, plus or minus 4%, so on. That's where we were in 2003. Here's where we are in 2006, and I haven't put the 2007 and 8 data in here yet. And we're getting extremely precise in these kind of measurements now in terms of our observation. And so we've got to where we got the fingerprint of the universe. That is back to the CSI analogy, right? We've got this map of the sky, and we're comparing it to our theoretical models, and we're finding the one that fits, and we're comparing it, and that's the one that gives us this. And we've been doing a lot more precise measurements. So remember that picture I showed you of the South Pole? This is what it looks like at the South Pole today, right? There are 3 big sets of experiments for doing cosmic microwave background measurements. The South Pole Telescope, the BICEPT, and there should be another one on here that's replacing it. DAISY, which is now gone to Quad, which will eventually go to SPUD, and so forth. And it's Club Med, right? You don't sit out on the ice, you don't have outhouses, you live indoors, right? And there's bingo on Wednesday night. It's just, things are so much better. And so we're in the golden age of cosmology. We have really gone far, and we really have now a set of big questions. As Leon was saying, we're at a point where a lot of discoveries, we know what discoveries we have to make. We have to figure out what the hell these things are, because we already know what the universe looks like. Now we got to figure out how it got there even more precisely than we do now. Okay, thank you.